Okay, can everybody hear me in the back? Perfect. All right, thank you very much for attending. Yeah, this work is joint work between UPenn in the US and the LIP in France. And is essentially embodied into a library for the proof assistance that is dubbed CTrees or CTrees in short. And whose purpose is to represent, but of course also to reason about non-deterministic, recursive, and impure computations. But before getting into any details about the libraries or anything, it might trigger some flashback to some of you if you happen to be already there 3 years ago at the time in your deal, when Chappe presented at the time something that had a very similar title, except that the library was called interaction trees, and that the non-deterministic adjective was missing. So of course it's no coincidence, this work is very much as part of this more general project. And it's not meant to replace interaction trees, but it's more like one new tool is a toolbox of this semantic construction that we're trying to provide for users. And so I'm going to start more like to try to paint broadly to use the story behind interaction trees so I can situate where this new contribution lands. And so the objective of the project overall is extremely common, I guess, for this crowd, simply to try to model computations in a proof assistant. For us in particular, it happens to be the proof assistant. Except we have some desiderata that kind of constrain the way we do things. The first thing is that we wanted to have a reusable component that we could share across several formalization projects. And the second one was that, in particular among these projects, some of them were semantically not so complicated, so they are typically first order. And so we really wanted to at least be able, for simple cases, to get computational semantics for cheap. But maybe the most striking peculiarity that we are looking for is that due to the kind of work we want to do, we did not want to compromise with testing. So we wanted to be able to actually test the formal semantics we work with without the effort of managing both an interpreter and the formal semantics on the side. So we kind of wanted to have shallow embeddings of our computations in code. Of course, in terms of objectives, we typically wanted to prove optimizations or point transformations, so we should support terminations and native refinements. So that kind of allowed us to develop such a reusable library of components that help users to define and to reason about monadic interpreters. And interaction trees are essentially the basic block of this library. If we are very crude, there can be some that basically are just implementing two very standard ideas from the literature, which is essentially to combine the so-called free monad, especially like Kiseliov's flavor of it, with the delay monad by Capretta. So I'm just trying to give you an intuition about how it works and how we use this library to model languages. Well, the first idea, the free monad, is basically just an idea of having an extensible syntax. So we cannot take the perspective that an effectual computation is just arising from a signature of operation. So we formalize a defined in data structure that's called ITree, that is parameterized by a certain interface E and X. And you can think of it as just representing computations that may perform operations described as in E, and in order to compute a result in X. And as its name suggests, of course, this can be equipped with the structure of a monad. So you get the first notion of sequential computation, so you can start programming. If we make things very concrete to illustrate how it works, you take simply, let's consider imperative programs, and you simply see in programs at this stage as computation performing reads and writes. So if you take this tree of program, the way it ends up being modeled typically by recurrence, and the syntax is going to start with a node representing the file to asking the environment to write something. And then, once the environment is done and acknowledge that it's done, the child of the computation will continue with asking this time the environment to read from the variable while, to which it will answer some natural number, for example, whichever notion of value you're manipulating. And because you do not know yet what value you will get, you continue with a continuation that will branch infinitely widely, explaining the computation no matter what is the answer. For instance, if you get 0, you will write appropriately 0 to X, and use this as a way to embed pure computations when your computation is terminated. I want just to emphasize why do we think of this as a syntax. If it's not obvious, if you consider this even simpler program here that just store y to x, and its corresponding embedding as a tree, there's this idea that as in program, of course, there should be intuitively thought as semantically equivalent. We would like to have a representation of our computation that allows us to prove that, but at this stage of representation, they are not, because they are fundamentally different trees, they do different interactions. And this idea is that, however, we can then bring, in a layered way, more and more semantics to our structure. We're going to implement some of the operations into a maybe richer monad that will support equating more computations. So in particular here, that will move us toward the vision of our Impure that are now stateful computations. Very simply, intuitively, that would become now a map from an initial memory to a finite memory. And here, you can recover our stateful algebra, our state algebra and prove the equation we want. So typically, that's how we build semantics with interaction trees, except that for more complicated language, instead of just having two steps of representation, we would have a layered sequence of interpretations. However, of course, this is hiding the main difficulty, which is we can't write interpreters for general programs in code so easily because we have to terminate. So that's where Capretta's dilemma comes in. It essentially allows you to internalize divergence into a structure so that you can pretend that you can write diverging programs. So if we just think of the trivially diverging program right through the skip, you need some kind of representation for this program. And again, you want to be eventually able to extract an interpreter. You have to do this in a constructivist way. So instead, you move into a coinductive structure. So your trees can be now potentially infinite. And you need to introduce one specific constructor, with a later constructor, that allows you to encode the fact that something happened internally. And in particular, for instance, internally, you can encode the fact that you have re-entered your loop. And this is sufficient to write fixed point combinators that allows you now to really program as if Coq was allowing you to diverge. Okay, so you have sequence, you have iteration. And if you just come back to the simple program that we have, the slight subtlety that comes in now is that since now you have potentially infinite trees, when you will interpret the effect, you now represent Impure not just as stateful computation, but as stateful delayed computation. And in particular, they may now disagree on the amount of internal computation that is necessary to reach the result. So they might have different numbers of later constructors in the tree that is mapped to a given initial memory. And therefore, in order to reason equationally about this computation, you need something a little bit more subtle than before. And so that's essentially one of the central components of this interaction trees, which is to define the right equivalence relation that you need to reason about this object, which essentially is a structural coinductive-inductive relation. So this was basically the state of things and gives you the ability to model languages or to reason about them equationally. And there is more complicated things that are added on top of it in order to reason about refinements rather than simply equivalencies. We were quite satisfied that it has been fairly successful in the sense that it has indeed been reused to model different projects in a fairly wide variety. For instance, there is a verified web server that has been modeled using interaction trees, internet representations of LLVM, or some work on verifying transactional objects. Actually, if you saw the excellent talk about conditional compositional refinements by Yongzhou, he also mentioned that he was using interaction trees. Okay, so this was kind of the context of this work. And the question is, what do we solve now with the trees? It's basically answering this very simple question, which is like, okay, this story about building your interpreters in a monadic way, does it still somehow work when you have non-deterministic computations? And in order to explain our answer, let's maybe take very concretely the same simple int program, but let's add a simple construction, BR C1 or C2, with intuitively the meaning is supposed to branch either towards C1 or towards C2. If we are in this context, the philosophy is very well, I have a new effect, let's define one of these syntactic operations, let's call it pick, which essentially means I'm just going to ask the environment which branch it should take. So the continuation is indexed by a Boolean, and if the environment tell me is true, I will go to the model of C1, tell me it's false, I will go to the one of C2. But again, this is essentially syntax. So if I just try to commute my two branches, at this level of representation, I don't have any semantics, I don't have any algebraic laws, so I cannot equate them, which is normal. That was the same story when I was still working with my read and write events. So at this stage, basically, pick is not commutative, nor idempotent, nor associative. And the point of this work is simply to explain what should be the structure that we could use in order to implement pick into. So the same way, we use the state model transformer and the option model transformers to model other effects. Before getting into the exact answer we get, it's informative to look a bit more closely at what we mean by either branch can be executed. It's a very standard observation typically in process algebra, which is there is really two operational behavior that we can mean by this. One is to say that the system may become either branch. So for instance, BR C1 or C2 may become C1. But another interpretation is that the system may take a transition that is offered by either branch. So if C1 were to be able to step to C1 prime, then so would BR C1 or C2, or the same for C2. And this distinction, of course, has a lot of semantic implication, because if you just consider this simple program that uses BR to either start printing infinitely often and std out some information, or to get stuck. If you take the first semantic interpretation of BR, then it's in particular possible to become stuck. But otherwise, in order to become stuck, you would have, in the first place, to be able to step from stuck. So in the second interpretation of your BR construction, this has only one behavior, which is a reactive one. And I just want to emphasize that the point of this library is not to decide what is the right semantic, what is the wrong semantic, just to provide tools so that no matter what you're trying to model, you can use the library to model it. So we don't want to commit to any of its meanings. So in order to understand what do we think we need in our structure in order to provide these two possibilities, it's kind of enlightening to take a perspective of a label transition system. We're going to store on the left both of these options. We're just going to kind of add the option we started from. What if we still have an uninterpreted event? This essentially corresponds to being able to go either to C1 or to C2, but additionally observing which branch we took, whether we went to the left or to the right. I mean, from the perspective of a LTS, this essentially means that we have this initial state P, and that we can get either to stuck or to a reactive state, but in a deterministic way, with different labels on each branch. So either we observe that it asks the environment to pick and it answers false, or we observe we ask to pick and it answers true. So this, we still want to model this, because we still want to be able to reason about external function calls, for instance, or simply redundant event that we have not yet interpreted. So that's going to be our external event, very much like in ITree. If we look at the second case, here we have, in terms of the structure of the LTS, exactly the same structure. We can move either to be stuck or reactive state, but this time we don't really want to know that it's due to the answer of the environment. So just going to reuse the usual tau label from process algebra. And since we want to model that, and we're trying again to have a shallow embedding, we're going to keep this idea of working with infinite trees, but now we have a so-called stepping branch construct that we're going to write BRS. The last case is a little bit interesting because structurally the LTS that it represents is different. We don't have a fork in the LTS this time. There's only one transition that is possible. P might already produce the first print to get into a reactive state. But the fact that the LTS contains no forking is really due to my ability of understanding the underlying LTS of the subcomponent of BR. It's because one of them is stuck that there is no branch. And again, my goal is kind of like to take some deeply embedded syntax and to compute a representation, a shallow embedding inside of code. And this kind of introspection that would decide whether I should have a branch or not in my representation, I can't afford to do it because it can be arbitrarily complicated. So instead, I'm going to cheat completely. I'm just going to say, sure, I keep in mind that semantically in the underlying LTS there is no fork, but in my tree, I will still put a branching node, but I'm going to put a peculiar branch. I'm going to take it to call it a delay branch, BRD. Okay, and so if we just have this in mind, so just summed up exactly the data structure we work with. It's a coinductive data structure, still potentially infinite trees, but this time with libs for the pure values, external event for external interactions and interpreted events, stepping branches or delay branches. On top of this, we can again give a structure of a monad, of an iterative monad, so we can again have fixed point combinators. And in particular, we re-established the equational theory that all of these form a proper iterative monad in the sense that we are using for interaction trees before. Now, when I said that we re-established this, of course, that begs the question with respect to what equivalence. In order to get to the notion of equivalence, the intuition that we followed was, as much as for interaction trees we could afford to be purely structural, essentially because this was all about sequential computation, here things get a bit more tricky. So instead we should build on top of the huge tradition that process algebra has been developing since 40 years, and take really the perspective of a label expansion system. We're just going to recharacterize this intuition about ITs that we have. First, if I have a leaf, I'm going to explain that you can take a step to a stuck process by observing the value that has been computed. Now, when I say that I'm building the ITs, know that as much as I really want to have a way to construct a data structure, when I reason about equivalence, I don't care anymore about constructibility. I can just use things propositionally. For external events, I want to observe which answer I got because I really don't want to posit any semantics. So I can take a transition to any child, but observing that I ask a question E on the adequate answer. Now for the stepping branch, I can also go to any child, however, this time always with the third transition. And finally, this is the place where I have to pay back the fact that I cheated earlier. In order to find a transition from a delayed branching node, I have to be inductively to look for a transition inside of one of my children. So the definition of the LTS itself is inductive. Once I have the LTS, the benefit is that now I can just open my favorite book about process algebra and re-implement all of the standard notions. So in particular, when should two CTrees be deemed equivalent? Well, one equivalence is to talk about the strong bisimilarity of their underlying LTS. But of course, I can bring lots of other notions of either refinement or equivalencies. And in particular, we provide strong bisimulation, weak bisimulation, complete and normal simulations on trace equivalence. But most of the theory we provide currently is respect to strong bisimulation. So just to illustrate quickly the kind of things that we work with, this intuition about having an important commutative and associative choice that we started with, we recover it in particular on binary delayed choices, delayed branches, excuse me, with respect to strong bisimulation. One kind of counterintuitive peculiarity when you start working with this structure is that the unary delayed branch that can in particular be very useful to guard your cofix points actually can be ignored with respect to strong bisimulation. Because strong bisimulation is built on top of the LTS that itself is already inductive and already forgetting information. When you move on to weak bisimulation, you get to additionally ignore typically unary stepping branches. And the subtle consequences of manipulating either delayed or stepping branches is dug further in the paper. What kind of result do we obtain? And in particular, how does it fit into this more general interaction tree framework? Well, the first thing that initially we were starting with this idea, we were looking for a model into which we could interpret this peak event. Well, indeed, you can use CTrees as a target of interpretation. In particular, we prove that if you start with two ITrees that are equivalent with respect to this inductive-coinductive relation that we are used to using there, then it entails that their interpretation will be strongly bisimilar. But furthermore, of course, we can still add additional effects on top of the CTree structure. So from CTrees, you can still support interpretation. So while monads at this time has to internalize both divergence and this choice, this branching nodes. And finally, just as an observation, there is this idea that the game that we play on interpreting external events can actually define basically the same kind of construction, giving a monadic interpretation of the internal choice, which gives us some lenience to reason about basically refinements of nondeterminism, or in particular some notion of scheduler, but you can also still extract to OCaml and just run things. So beyond the meta series that we provide, we propose two case studies to illustrate how to use these structures. So the first one was a model of CCS, where we give a model of CCS processes in terms of these CTrees. So we have a shallow combinator for each of the construction of CCS, and we re-establish standard equational theory on up to principles for strong bisimulation for CCS, but directly with respect to the strong bisimulation inherited over CTrees. And to be sure that we define the right thing, we also prove that the strong bisimulation in terms of CTrees of the model is exactly the same equivalence as the operational traditional strong bisimulation. Very quickly, we also have an example that combines this time Stateful to reason about shared memory, or where here we consider a variant of int with the for construct on yield, and we show again how to represent this computation in terms of the CTrees, this time into 3 steps. First, we have a compositional construction that builds a sequential trees but manipulating for and yield events. Then a top-level interleaving combinators to introduce the nondeterminism and eliminate this event. And then we add state on top of it. And we prove a set of algebraic laws on this language. So, as a conclusion, our goal here was to add a new component to this interaction tree framework. So it's a new library that you can use if you like these approaches, where intuitively we want to keep the same kind of tree-like infinite structure, but adding 2 kind of branching nodes, and crucially stepping away from the very structural way we were thinking about equivalence before to a vision toward an underlying LTS in the tradition of process algebra. And we want to emphasize that this is an actively developed library. If you're interested, please take a look. And we also wanted to mention that this relies heavily on Damien Pou's work on the companion for all of the implementation side. Thank you very much.
So we have time for maybe 1 or 2 questions. Yeah, please.
Hi, Mitch Wan, Northeastern University. Have you considered modeling async await in this framework?
We have not yet, no.
You think it's trivial or?
Trivial for sure, no. That's at least one thing I can say. I don't have a good answer. I haven't thought about it enough, but that would be interesting to dig into.
Yeah, there is a question over there.
Hello, I'm Jeff Gillini from Cambridge University. So you mentioned going from ITrees to CTrees by interpreting the non-determinism. I'm curious, can you go from CTrees back to ITrees by fixing a particular execution trace, or maybe by actually having a predicate on a CTree saying, a deterministic CTree is an ITree, or something like that? And in particular, do you have reason to set ITrees that a CTree can produce and maybe do sampling?
So definitely, we haven't defined that at the moment, but we discussed it. It's definitely possible, yes, to characterize what is to be deterministic for CTrees in a certain sense, and then you can write a partial function back into itrees, and essentially prove that it will that the domain will be included, will contain the deterministic one. In terms of characterizing what are the itrees that correspond to CTrees, it's a little bit annoying in the sense that the problem of CTrees is that they have a lot of redundancies. There are many representations of different things. So for instance, if you have an infinite chain of delayed nodes, then it's actually a way to represent the stack computation. So there are lots of redundant representations of various computation. So I can clearly characterize what is it, how do I embed, how do I inject itrees into CTrees, but it's a bit harder to characterize the reverse order, but it should be possible.
All right, so I would suggest you take the question offline just in the interest of time.